everyone, welcome back to another video. Today we're going to be going over the advanced math content area for the SAT and PSAT exam. As we can see here, we have a lot of topics to go over, and each one of them is pretty important, so please make sure that you're going through this area and understanding it as we go through it. So let's go ahead and get started with the first topic of factoring quadratic and polynomial expressions. So for quadratic expressions, remember that quadratics are in the form like x squared, well, it's really ax squared plus bx plus c. So when it comes to factoring quadratics, we typically have a trinomial that we're given, like let's say x squared minus 10x plus, let's pick one with a better factor actually. X squared minus, we'll do 9x plus 18. So let's say we're asked to factor this quadratic equation. So how do we do this first? Let's first figure out what terms will get us this x squared. Because what we're trying to do is we're trying to split this trinomial into two binomials. That's basically the idea of what we're trying to do. So what we would do is x squared can be broken down into x times x, which makes sense since that's really the only way you can get x squared, because you don't want to have x squared and 1, so it's just x and x, so that way we get binomials with degree 1. And then what we're going to do is we're going to look at our constant term here, because our factors are going to have to multiply together to give us this 18. Now, since our constant is positive, that means that our factors are going to be the same sign as our b term, which in this case is negative. So we can already take care of that. If this was negative, like it was minus 18, then it's plus minus or minus plus for the factor signs. Okay, so we're going to look at factors of 18, right? So what are our factors of 18? We have 1 and 18, 2 and 9. And that's it. Obviously, you have 9 and 2, 18 and 1, but those are basically interchangeable because this is multiplication, and we have the same sign. If it's different signs, then obviously which number you put where does matter. So in this case, we want to figure out from these factor pairs which ones will... Oh, sorry, there's also 3, 6. My bad. We want to figure out which ones will sum up to 9. That's basically what we want. So 1 plus 18, that's not going to give us 9. 2 plus 9, that's not going to give us 9, but 3 and 6 will. So it's going to be x minus 3 and x minus 6. It can be in any order. It doesn't matter what's the order. So x minus 3 times x minus 6, that would be your factored form of this trinomial. And later when we do operations with polynomials, we'll talk more about how to multiply binomials together using the FOIL method. But as of right now, this is how you would factor this trinomial. Sometimes you'll get problems that require you to factor a trinomial where the leading coefficient is greater than 1. So I'm going to try to think of an example. Say we have 2x squared, and then we have minus 5x minus 3. That should work out, yeah. Okay, so typically when you're given a trinomial where the leading coefficient is greater than 1, you first want to see if there's a common GCF that's greater than 1 in the terms to see if you can factor out to make it a little bit easier to help you factor the trinomial. We don't really have that in this case since the greatest common factor of 2, 5, and 3 is just 1. So what we're going to do is we're trying to break this into two binomials. What factors will give us 2x squared? Well, there's really only one combination, 2x and x. Now, we're going to look at our constant next. Our constant is negative 3, so it's negative now. So that means we're going to have plus minus for our two signs, and it does matter where those plus minus signs are. We can't put them anywhere we want, so we're going to hold off with signs for just a second. All right, so what are our factors of 3? Well, thankfully, it's just 1 and 3. But we need a pair of 1 and 3. Well, one of them is going to be positive, one of them is going to be negative. So it's either 1 and negative 3 or negative 3 and 1. Which one will sum up to negative 5? Now, here we have a little catch because we have a 2x here. So it's really going to be like which one, when you apply the 2x, is going to get you to negative 5, if that makes sense. So if we have, let's say, the plus 1 here and the minus 3 here, right? If we do 2x times negative 3, that'd be negative 6, plus 1. That would work for negative 5. So if we have it like this. And just to test it, if we had plus 1 here, it'd be plus 2 minus 3, which would be minus x, which would not work for this one. So this is how you'd factor it into 2x plus 1 times x minus 3. To get this b term, that's based off of the multiplication of these two together and like adding them together, since they'd be common like terms, since they both are x terms. So it'd be negative 6x plus x, which does get you negative 5x. So that would be your answer for factoring out this trinomial. All right. So that's the idea behind factoring out quadratics. There's one other type of factoring that I want to go over called factor by grouping. Basically, you'd have something like, I'm trying to think of a good one, like x cubed minus 5x squared. And then we do plus 25x. Actually, not a plus. We want to make this a minus. And then minus 125. I think this would work out. Okay. So basically what we're trying to do here is this. No, this would actually be a plus. Okay. So what we're trying to do here is this. We're trying to, what we're going to do is we're going to kind of like split this up into two terms, right? Two groups of two, basically. And we're going to try to find a common, what's the greatest common factor in x cubed minus 5x squared? Well, it'd be x squared. So it'd be x squared times x minus 5. That makes sense. We're pulling out an x squared, so we're left with 1x and then minus 5. And then now, what's the greatest common factor in minus 25x plus 125? So in this case, we're going to do minus 25. And there's a reason why we want to do minus 25 and not positive 25. So when we do that, we'd have x minus 5. Now, I did minus 25 and not plus 25 because we want these inner terms to be equal to each other, or inner factors, basically. So x minus 5 is a factor of this big polynomial. And we can rewrite this as a factor. So we'd be basically left with x minus 5 times x squared minus 25. And you can actually break down x squared minus 25, which is actually a good thing we got to this. This is called difference of squares. Whenever you have a difference of squares like x squared minus 25, you can break it down. What's the square root of 25? That's 5. So x minus 5 and then x plus 5 to represent like the two different factors. Like if you were to take the square root of 25, the two different square roots, plus 5 and negative 5. So this would be your answer to fully factor out this original polynomial up here at the top. So that would be if you have difference of squares. That's very important. And then one more thing with perfect square trinomials, if you have like x squared minus, well, I mean, maybe we could, yeah, we'll just do it like this. So x squared minus 10x plus 25, right? We can break this down into x minus 5 squared. If we have x squared plus 10x plus 25, we can have it as x plus 5 squared. So basically, if you have a factor and you see that the b term is double it and the c term is the square of it, then it's going to be that factor squared, basically, your perfect square trinomials. Oops, really bad star there. This would work. Okay? All right, so that's basically for quadratics and polynomial factoring. Let's move on to the next topic of radicals and radical exponents. So when we talk about exponents, we're actually talking about like fractional exponents and radicals. So basically, if you have, it's important to be able to convert between, fractional exponents and radicals. So when we have radical of x, right, what does this represent? Technically, the square root sign is like has an index of 2, right? We don't usually write that because when we just see a root by itself with nothing, we automatically know it's a square root. But it's like x to the power 1, and you're having a square root with an index 2. So we can rewrite this actually as x to the power of 1 over 2. So this is how we convert. This denominator of the fractional exponent is your index of the root, and this numerator of the fraction is going to be the actual exponent that your base is raised to inside the radical. So another example, let's say we have the cube root of x to the fourth. If we were to rewrite this as a fractional exponent, it would be x to the 4/3 power, okay? So that's how you convert between radicals and fractional exponents. I'm going to probably take time here because I don't think we have it in the later thing. I'm going to take time here and go over exponent rules really fast. So exponent rules, if you have the same base and you're multiplying two exponents together, different exponents but the same base, you're going to add the powers together like this. So like x to the a power times x to the b power is x to the a plus b power. If you're dividing them, same base, different exponents, you would subtract the exponents like this. If you have like x to the power a and you're raising it to another power, aka power to a power, it would be x to the a times b power. Okay. If you have x to the negative, like if you have a negative exponent, you can rewrite it as 1 over x to that number, x to that exponent. So if you have a negative exponent, you just move it to the denominator, basically. And then finally, if you have any number raised to the 0 power, that would be 1. So these are the major exponent rules you guys should know. I'm covering it now because I don't think there's any other place here that we're going to cover, and these are very important to know. All right, moving on to the next topic of operations with polynomials. So we're going to basically be doing adding, subtracting, multiplying, and dividing polynomials. So adding polynomials and subtracting polynomials is pretty easy. What you want to do is you want to take the terms that are like terms and you want to combine them together when you're adding or subtracting. So for example, if we had like 10x squared plus 5x minus 3, and we were adding it to 2x squared plus 2x minus 1. Right, when we're adding, if you really wanted to help you visualize it, you can have this addition be vertical. So then plus 2x squared plus 2x minus 1. And then you can basically go down the line. 10x squared plus 2x squared is 12x squared. 5x plus 2x is 7x. And then plus, sorry, it was a minus 3, not a plus 3. And then minus 3 minus 1 is minus 4. So like this. So you're just adding like terms that share the same degree. So x squared, x terms, and then the constants. And then, actually, I don't want to erase this all the way. We could just erase this. I'm going to use the same problem, but we're going to do subtraction now. I'm going to erase my answer, obviously, because it's going to be different. So minus and then minus. I'm going to put a parentheses around this so I'm not confused with signs. So basically 10x squared, now it's going to be minus 2x squared. We get 8x squared. 5x minus 2x is going to be plus 3x. And then negative 3 minus minus 1, two minuses make a plus, so negative 3 plus 1 would be negative 2. It's like this negative is almost like distributed to each one of these terms. All right? So that's how you add and subtract polynomials. It's pretty simple. Multiplying and dividing, that's where things get a little bit more tricky. We're first going to do foiling, which is multiplying two binomials. We just did factoring polynomials, so we're going to do it like the opposite way. So if we have, let's say, x plus 3 and x plus 4, and we are supposed to multiply these binomials together, right? What we want to do is we want to follow the mnemonic FOIL. What does FOIL mean? It means first, which are like the first two terms in each binomial. Then outer, which would be the two outer terms in the binomial. So the first term on the left and the last term on the right. Inner, the two terms that are the closest together in the binomials. And then last, the other terms that we haven't accounted for, the last ones, which are usually the constants. So first, outer, inner, last. So when we do that, we're going to get x squared plus 4x plus 3x plus 12. Which we can simplify these like terms to get x squared plus 7x plus 12. So that's how we do foiling. It's first, right, these terms first, the x and the x, right, they form together to become x squared because it's like x to the 1 times x to the 1, which is x squared. Then the outer with 4 times x plus 3 times x, that's just 4x and 3x, and then the constants 12, you get x squared plus 7x plus 12, okay? So that's the idea behind foiling. It really doesn't matter whatever coefficient you have in front of the x. It's the same process. All right. I don't think you guys are going to have to worry a lot about multiplying trinomials but we can quickly work through a process of that. Let's say we have x squared plus 10x plus 5 times x squared minus 3x minus 6. So here's how we're going to do this. We're going to do kind of like a grid method to multiply these trinomials. So x squared, 10x, 5, I'm going to write these terms separately out at the top for the first polynomial, and then I'm going to write the terms for the second polynomial here on the side, making sure that I include the signs. So now we can imagine this almost like a grid, like this, okay? So we're going to be trying to find an answer for each grid, right? The two terms that like bound it, for example, so for this left square, we have x squared times x squared, and we're just going to multiply, and then we're going to add them together to get our answer. So x squared times x squared is x to the fourth. X squared times 10x is 10x cubed. X squared times 5 is going to be 5x squared. Negative 3x times x squared is negative 3x cubed. Negative 3x times 10x is negative 30x squared. Negative 3x times 5 is negative 15x. Negative 6 times x squared is negative 6x squared. Negative 6 times 10x is negative 60x. And then negative 6 times 5 is negative 30. So now we've done our grid multiplication, and now we're going to combine like terms. Luckily for us, combining like terms are always done in a diagonal. So we can see here we have the x cubed terms that we're going to be combining, the x squared terms that we're going to be combining, and then the x terms that we're going to be combining. So I'm going to write it out here on the left, our answer. We're going to have x to the fourth, and then 10 minus 3, that's going to be plus 7x cubed. And then 5 minus 30 is negative 25, minus 6 is negative 31x squared. Sorry for it not all fitting in one line. Actually, we don't want a plus here. Negative 15 minus 60 is going to be minus 75x, and then minus 30. So that would be your answer. Again, I don't think you'll get this on the SAT or PSAT, but it's just good to know. All right, and then we're going to talk about division by polynomials. There's two types of division we're going to talk about. Polynomial long division, and then synthetic division. So we'll start with synthetic division first. Basically, with synthetic division, you have a formula, like let's say like this, right? And this is the same one that we did earlier, but let's say we have x minus 5. We want to actually check that this is, in fact, a factor for this polynomial. So here's what we're going to do. We're going to set this factor equal to 0. We're going to get x equals 5. We're going to have this number 5 in like the corner here. And then we're going to write out the coefficients for each of these terms for the original polynomial. So we have 1, negative 5, negative 25, and 125. And I just want to make it clear, if you had a polynomial where it skips a term, so like if it goes from like x cubed straight to x, like there is no x squared term, you got to put a 0 for the coefficient for that x squared term. So we have the coefficients written out here at the top. I'm going to pull this 1 down here, and then we're going to start. We're going to do, we're going to do 5. We're going to do 5 times 1, that's 5. So negative 5 plus 5. Now we're going to be like adding. Negative 5 plus 5, that gets us 0. Then 5 times 0, that's 0. Negative 25 plus 0 is going to be negative 25. And then I'm going to do 5 times negative 25 to get me negative 125, which when I add it, I get 0. So this last term here is very important because that's the one that tells you whether or not this is a factor or not. Now, obviously, we know that x minus 5 is a factor of this polynomial. I picked this polynomial for a reason. This being 0, this basically means the remainder. This is the remainder spot. Basically, the remainder being 0 says that, yes, x minus 5 is in fact a factor of this original polynomial. If you had any value there other than 0, then it's not a factor. There's a remainder. And then if you pretended that you didn't know the remaining roots of this polynomial, you could like carry down basically like now this 1 is your coefficient for your x squared term. This is your coefficient for your x term, and this is your constant. And you could figure out you're down to an x squared. It's pretty easy to factor from this point. All right, so that's synthetic division. Polynomial long division is something you do if you can't really do synthetic division. So like, for example, if you have x squared minus 5x plus 5 over x plus 3. Okay. You could do synthetic division here, but we're gonna do it using long division because it follows the same process basically. It's just I feel like synthetic division is a little easier, but I want to illustrate to you guys how to do polynomial long division. So here's the big idea behind long division, right? You're going to start with this x squared term, this first term in the dividend, and you're going to divide it by x, the first term in the divisor. So x squared divided by x, that's going to be x, okay? So now what we're going to do is this. We're going to multiply x times x, right? That's going to be x squared. And we're putting a minus sign here because we're trying to cancel out the x squared term. But now we're going to do the same thing with 3, right? 3 times x. 3 times x is going to be 3x. We're not doing x squared divided by 3 because you can't do that. So you're taking the second term in the binomial and you're multiplying it times that quotient x on the top. So 3 times x is 3x. Now we're subtracting what we got here. So x squared minus x squared is going to cancel. We have negative 5x minus 3x because this minus is being distributed in. And we're going to get minus 8x. And we're going to bring down this plus 5. So now, same process. Negative 8x divided by x. That's going to be minus 8. So when we do x times negative 8, we're going to keep this negative sign in here. Negative 8x. And then 3 times negative 8 is going to be minus 24. So again, this is going to cancel out. And then we're going to get plus 5 plus, right, minus is a plus, 24, that gets you 29 as your remainder. So this is our remainder. We're not going to do it again because 29 divided by x would not work. So x minus 8 is our quotient, and then plus 29 is our remainder, but we're dividing it over x plus 3 because, right, that's why we stopped, because this isn't something that can be simplified. So this is our remainder. And this is our quotient. So that's how you would do polynomial long division. All right, let us move on to the next topic of operations with rational expressions. So for these ones, it comes down to the idea of being able to, like, if you have like two rational expressions in the numerator and denominator, you being able to cancel out factors, for example. So let's say we have x squared minus 10x plus 21 over x squared minus 6x plus 9. And we need to simplify this. Now, on surface, it might be like, okay, maybe we need to do long division or something. But we don't. We don't actually have to do that. We can actually break down both these trinomials into their respective factors, the two binomials that multiply together to get the trinomial, and we'll be able to simplify it like that. So x squared minus 10x plus 21, right? What does that break down into? So obviously x squared is going to just break down into x and x. Our factors of 21 are 1 and 21 and 3 and 7, right? It's going to be minus signs because our constant is positive and our b term is negative. So is 1 plus 21 giving us 10? No. 3 plus 7 is, though, and again, it doesn't matter which factor has 3, which factor has 7. All right, how about the bottom now? For 9, okay, obviously, let's write out our factors. We have x and x for x squared. For 9, our factors are going to be 1 and 9 and 3 and 3. So which one of these factors will sum up to 6? 1 plus 9, is that equal to 6? No. 3 plus 3 does work, though. And again, it's minus signs. We already know that. And it's minus 3 and minus 3. So you see how we have an x minus 3 in the numerator and denominator. We're going to go ahead and cancel this out. So we are left with x minus 7 over x minus 3, which is the furthest you're going to need to simplify. You don't need to do long division. It's not going to help because you're just going to get 1 and then with the remainder. So this is your simplified answer. That's basically what you need to do with rational expressions. However, there is a little bit more to it than this. Obviously, this is just simplifying them. What if you need to like add or subtract them? Rational expressions. So for example, let's say we have 1 over x plus 5 plus 1 over x plus 3. How would we be able to add these together? So we want to find a common denominator. It's very similar to like adding a fraction, right? You obviously can't add these straight up because they're different factors. So we need to find a common denominator. And in this case, the common denominator is just these two numbers multiplied together, x plus 5 times x plus 3. So if we were to multiply each, we want to multiply each fraction to get to this common denominator. So in other words, we're multiplying this fraction by x plus 3 on the top and bottom, so that way it's still legal, because technically x plus 3 over x plus 3 is just 1. And then we're multiplying this times x plus 5 over x plus 5. So when we do that, we get x plus 3 over x plus 5 times x plus 3 plus x plus 5 over x plus 5 times x plus 3. And then now we can combine the numerators. X plus x is 2x, 3 plus 5 is 8. So we get 2x plus 8 over x plus 5 times x plus 3, which would be the answer here. And if we were subtracting, it's the same idea. You want to find a common denominator. You would subtract it. You'd get negative 2 over x plus 5, x plus 3, because x minus x is canceling it, and then 3 minus 5 is negative 2. So when you're adding and subtracting rational expressions, you would want to make sure you get a common denominator first, and then apply the operation. If you're doing multiplying and dividing these rational expressions, though, it's a little bit easier. If we want to work with our same example of 1 over x plus 5 times 1 over x plus 3, you would just multiply these straight through. That would be your answer, right? Numerator times numerator, denominator times denominator. If you're dividing these, it's still not very difficult. Remember, when we divide fractions, we're doing keep, change, flip. So we want to keep the first fraction of 1 over x plus 5. We want to change this division sign into a multiplication sign, and then we want to flip the second fraction into x plus 3 over 1, and then you just multiply it straight through x plus 3 over x plus 5. So multiplying and dividing rational expressions is pretty easy. All right, let us move on now to the next topic of nonlinear functions. So what are nonlinear functions? We're basically going to be talking about regular functions, but they're not like linear. They have higher degrees, like x squared plus 2 or x cubed minus 1, stuff like that. And specifically what we're going to be talking about here is just how to, like, you know, plot them, and then also we're going to talk about composition of functions. So whenever you get a polynomial like this, if you're given like a table, and let's say you need to find like certain values, like let's say 0, we're using this function, right? And let's say we have like 0, and then we have 0, and then we have 7, and we want to figure out what are the appropriate input and output values for these three, right? So we see x is 0 to start off with, so we're plugging in f of 0 is 0 cubed minus 1. So it'd be 0 minus 1, which is negative 1. That would go here. For this one, we're given an f of x of 0, so 0 is our y value, and we have x cubed minus 1. Add 1 to both sides, we get 1 is equal to x cubed, so x is 1. 1 would fit here. And then here we have another output, 1, 7 equals x cubed minus 1. Add 1 to both sides to get 8 equals x cubed. X would be 2. So that would be how you fill out this table. And then obviously to graph, you guys know how to do that. Let's talk about composition of functions really fast. What is composition of functions? Basically, you have two functions. Like let's say f of x is x squared plus 1 and g of x is 10x. And you're going to see composition of function either like this, so like f of g of x. So it's like almost like you're plugging in g of x into f of x every time you see x. Or less common, but you might see it like this. But we're going to refer to it as the first type. So what does this mean? We're plugging in g of x anytime we see x in f of x, right? Because that's what it's doing. It's basically taking the position of an x. So f of g of x, right? We're plugging in g of x anytime we see an x in f of x. So we have an x here, so it's going to be 10x and then squared plus 1. You could simplify this to 100x squared plus 1. But that's the idea behind composition of functions. So know how to do composition of functions. If you have to check that they're inverses, basically f of g of x and g of f of x, which is basically you're plugging in f of x every single time you see x and g, those should both be equal to x. That's the only way you can determine that they're inverses from composition of functions, and sometimes it's better than actually like, switching the variables and whatnot. So that's the idea behind composition of functions. All right, moving on to the next topic of isolating quantities. So isolating quantities, this is just about, you'll be given like a random equation with variables, and you're gonna have to like solve for a particular variable. Like if we have area equals length times width for a rectangle, for example, and let's say we want to find the width. What is W? How do we isolate W? We divide both sides by L. So W is equal to A divided by L. That's really the idea behind it. It's just being able to actually isolate particular variables that aren't like numbers, right? Another example, if we have like distance equals rate times time, and we want to solve for the rate. How do we solve for the rate? We need to isolate it by dividing both sides by t to get d divided by t equals r. So that's kind of the idea behind isolating quantities. It's pretty simple. Just know that you're not going to get numbers for these, but it's okay. Even if it's in letters, you're still following the same steps to solve for the particular variable that you're trying to isolate. All right, next topic is solving quadratic equations. So for solving quadratic equations, basically you will be given a equation, like let's say this, 10x plus 26 equals 1, and you want to just solve for x, right? So the easiest way to do these kind of problems is try to get it in the form of like a standard quadratic. So we want to basically have it equal to 0 on the right-hand side. So I'm going to subtract 1 from both sides, and I'm going to get x squared plus 10x plus 25 equals 0. So here, I know that this is going to be a perfect square trinomial because 25 square root is 5, and 5 times 2 is 10, which gives us this middle b value. So the answer is going to be x equals -5 for this case. So that's the idea behind quadratic equations. I can try to pick another one that's a little bit more work. Let's say we have x squared. Let's do minus 4x plus 6 equals x. Actually, no, not this. Let's do plus 4 equals x minus 2. Okay? You're still working under the same principles. We want to get this right side of the equation equal to 0. So I'm going to subtract both sides by x and add 2 to both sides. So when I do that, I get x squared minus 5x plus 6 equals 0. And then I'm just going to factor. Remember, it's x times x to get x squared. 6, our factors are going to be 1 and 6 or 3 and 2. We can already put minus signs because it's a positive c and a negative b. And 1 plus 6 isn't going to get us 5, but 3 and 2 will. So if you were to set each equal to 0 and solve for x, we get x is 2 and x is 3, which would be the answers for these equations. All right? So that's the idea behind solving quadratic equations. Let's move on to linear and quadratic systems. Also, by the way, before we get onto that, let's actually go over quadratic formula really, really fast. Quadratic formula is how you can solve a quadratic equation if you are not given a nice factorable one. Basically, this is your quadratic formula of -b, where you have your, assuming you have a trinomial ax squared plus bx plus c. It's -b plus or minus the square root of b squared minus 4ac over 2a. So this is important. For example, if we had 2x squared plus 10x plus 4, no, actually plus 3, and we want to solve this by quadratic equation, it'd be minus 10 plus or minus the square root of 10 squared minus 4 times 2 times 3 over 2 times 2. We can simplify this to -10 plus or minus the square root of 100 minus 4 times 2 times 3. That's going to be 24 over 4. -10 plus or minus the square root of 76 over 4. We can actually simplify this radical to -10 plus or minus the square root of 4 times 19 over 4, which we can break down into -10 plus or minus the square root of 2 root 19 over 4. And then you can cancel the terms by 2 to get -5 plus or minus root 19 over 2. So those would be your factors. Use this formula if you cannot factor easily. All right? Okay. Now let's move on to linear and quadratic systems. So Linear and quadratic systems, what does that mean? Basically, you're going to be given like a system of equations like y equals 5x and y equals x squared plus 5, and you're going to have to figure out the solution for them. You can either graph these or you can just try to solve them like a quadratic equation. I would probably want to do the equation more than graphing, I'm not going to lie. So I'm going to set these two equal to each other because they're both solved for y. So I get 5x equals x squared plus 5. I want my a term to be positive, so I'm moving 5x over to the side, to the right side. I get 0 is x squared minus 5x plus 5. I don't really think I can factor this easily because 1 plus 5 is going to give me 6. So we're going to use quadratic formula. So negative b plus or minus the square root of b squared, 25, minus 4 times 1 times 5 over 2 times 1, which is 2. We can simplify this to 5 plus or minus the square root of 25 minus 20 over 2. 5 plus or minus the square root of 5 over 2. So that would be the answer for this system. If you were to plug them in for x, you would get the same y value. So that's the idea behind linear and quadratic systems, okay? You'll just be given a linear equation and a quadratic, and you're going to need to find the solution. Usually just make it into a quadratic equation and then use quadratic formula or factoring if you can. All right, on to the next topic of radical, rational, and absolute value functions. So what are radical equations looking like? They would look like something like, let's say, square root of 2x equals 5, for example. So we want to solve for x. So to do this, we are going to square both sides, right, like this, to get rid of the square root. So we're going to get 2x equals 25, and we're going to divide both sides by 2, and we'll get x is 12.5, or 25 over 2. That's basically all you need to do for radical equations. I'll give you guys a slightly harder one. Square root of 2x minus 4 equals 8, and we want to solve for x. Again, we want to get rid of the square root first, so square both sides. We're going to get 2x minus 4 equals 64. And then we're going to add 4 to both sides. We're going to get 2x is 68. So x is 34. All right? You don't need to worry. Like, I know sometimes it will be like, okay, when we take the square root of 64, we should have like 8 and negative 8. But you're squaring in this case, so it doesn't really matter as much. If you do get into a situation, because remember, whatever is inside this radical, it can't be less than 0, because then you're going to deal with complex numbers, which we're not going to get into in this video, I think. Honestly, I might actually touch on it right now, to be honest, because that is important. So if you do end up getting a situation where you have like a negative underneath the radical, so you have like negative 10, like a negative number underneath the radical, right? What exactly do we do? Because technically you can't take the square root of a negative number. This is where we get the concept of I. I is your imaginary number. It's equal to the square root of negative 1. Typically, the only versions of I you're going to need to know is I is square root of negative 1. I squared is negative 1. I cubed is going to be negative I. And then I to the 4th is going to be 1. Okay? So those are the main ones that you're going to need to know, right? I cubed is because it's I squared times I. So that's just I squared is negative 1, so negative I. Try to remember these. If you're dealing with like adding, subtracting, multiplying, dividing complex numbers, they're typically going to be in the form a plus bi, where this is your real number, a is your real number, b is your imaginary number. If you're adding complex numbers, you're adding the real components together and the imaginary components together, so it'd be like 4 plus 7i. Subtracting, you're subtracting the real, subtracting the imaginary. If you are multiplying complex numbers like these together, you're following the exact same steps as FOIL, just remembering that you are going to get an I squared when you multiply these terms, 5i plus 2i, and remember I squared is the same thing as negative 1. So it just becomes a constant that you're going to add on to this 2 times 2. And then if you're dividing complex numbers like this, it's going to be a little bit challenging. You're going to have to multiply times the conjugate Conjugate meaning you're just flipping the sign of your denominator. So you're changing from 2 plus 2i to 2 minus 2i, and then you would do foiling again. You'll get a real number in the denominator, and then a real and imaginary component in the numerator. All right, so that was a really quick lesson on complex numbers. I did not think I covered that in any other videos, and it's also an important topic that you might need to know for the SAT. You might get a couple questions on those, because that is in Algebra 2. All right, so that's the idea. That's the main idea behind radical equations. Rational equations is the next thing, right? Yeah, rational functions, actually. I should call it correctly. Rational functions. Basically, you'll have something like, 1 over x plus 3 equals 2 over x plus 5. How do we do these? We're going to cross multiply, like this. So x plus 5 equals 2x plus 3. Then we're going to distribute on the right-hand side. So x plus 5 equals 2x plus 6. We want to get the x's on one side and the constants on one side. We want the x to be positive if possible. So we're going to move actually our x's to the right. And then we're going to move our constants to the left. And we're going to get negative 1 equals x. So that would be the answer here. Okay? Your solution, you want to make sure that you're not getting an x where the denominator equals 0. So if we got like a negative 3 or a negative 5, for example, that would be called an extraneous solution. Basically, you got it when you solved for the answer. But if you were to plug it back in to the original equation, right, you'd get 1 over 0, for example, and you can't divide by 0. That's not allowed. So that's just a tip. We didn't have to deal with it in this problem. But for rational equations, if you do get a solution where if you were to plug it back into the original equation, you're getting a 0 in the denominator, then that's not correct. If you were to do also a logarithm equation and you're getting a negative inside for your base, that would all negative for, I'm sorry, not the base, but the inside value, that would also be incorrect. Remember that you need to follow math rules even when you're solving for stuff like this. So that's basically rational functions. Absolute value, you'll have something like 3x plus 5 equals, I'll do a hard one, x plus 2 minus 5. It's mainly the same idea. Actually, no, I'm not going to do this hard one, actually. I don't think you're going to get something this hard. 3x plus 5, and then we'll have it equal to 10. It's mainly the same idea as regular equations. However, it's absolute value. So technically, you're going to have to consider both positive 10 and negative 10 for solutions. So basically, we can rewrite this as 3x plus 5 equals 10, or 3x plus 5 equals negative 10. Remember, it's absolute value. So if you were to solve, we're going to solve each one. So let's actually do that first before I start getting ahead of myself. So subtract 5 from both sides. We get 3x is 5. Divide both sides by 3 to get 5 over 3. Here, subtract both sides by 5. You get 3x is negative 15. X would be negative 5. So when we plug this negative 5 back in for x, yes, we will get negative 10. But remember, absolute value, anything in the absolute value bars is going to be positive. So negative 10 in absolute value bars actually becomes positive 10. So that would be an answer for this equation. All right. Typically, that's about as hard as it's going to be for absolute value functions, I believe, on the SAT or PSAT. All right. Next topic. Let's go on to quadratic and exponential word problems. So these are basically just going to be kind of similar to what we've been going over in terms of just taking concepts that we know and turning it into word problems. Like for example, an exponential word problem you might have to do with population growth or decay. So when you have a population growth or decay problem, it might be something like this, right? This is your initial value, this is your rate, this is for time. So for example, if we live in a town that let's say has 10,000 people originally, and it increases by a rate of 2% every year, what is going to be the town's population in 5 years? So this is our original value that's going to go in here. This is our rate, which we're going to convert to a decimal and put into here. And this is our time, which is going to go here. So we're going to have P equals 10,000 times our rate, which is going to be this as a decimal, 0.02. Remember, to convert from percentages to decimals, we're doing 2 divided by 100. So we get 0.02, and then we're raising it to the 5th power to represent, because since 5 is our time. So now it's just a question of using your calculator and coming up with the answer. So I'm going to go to my calculator here, and I'm going to do 0.02 to the 5th power. And when I do that, hold on one second. So it's actually increasing by 2. My bad. It's increasing by 2% every single year. So you actually want to include this 1.02. My bad. Because it's growth. Remember, when it's exponential growth, your R needs to be greater than 1. If your R is between 0 and 1, it's decay. All right, my bad, guys. Apologies about that. So it's 1.02 to the 5th power. And then we're going to multiply it times 10,000. And we're going to get approximately 11,040 as our answer. Typically, if this was a multiple choice, the answer choices will be spaced out, so you'll be able to pick the one that's closest to. Really, it's like 0.808 added on, but we don't need to worry about that. All right? So remember, if it's exponential growth, your R needs to be greater than 1. So if it's increasing by 2%, it's really like 1.02. My bad. Sorry about that. All right, so that's your exponential word problem you could get. A quadratic one is just like if something is changing at a faster rate, like if it's like, like x squared plus 5, and you want to see like how much is something changing, like if it's changing at this rate, like how much is it changing when x equals 2? You just do like 2 squared plus 5, you get 4 plus 5 equals 9. Other quadratic word problems you could get is like where you have like an equation and you're going to have to like factor to find the x. You're following the exact same steps that we've been doing for solving quadratic equations. It's just now, can you look through a word problem and pick up the most important information to help you get the correct answer? So that's the idea behind quadratic and exponential word problems. Quadratic graphs and exponential graphs, we're going to do those together actually. So quadratic graphs, right, quadratics are typically, they're like this U-shaped. So this U-shaped, this is like y equals x squared, for example. Our A term determines whether our parabola opens up or down or left or right. If you're doing, like this would be x squared equals y squared. If our A term is positive, our parabola is going to be opening up. If our A term is negative, our parabola is going to be opening downwards. This would be y equals like negative x squared, for example. And if it's opening to the right, it would be positive. And if it's opening to the left, it would be negative. All right? But the main idea of where we talk about quadratic graphs comes into the different forms we can write quadratics as. We can write it in standard form, which is this y equals ax plus bx plus c form. We can write it in factored form, which is basically our roots. Or we can write it in vertex form, where it's like ax minus h squared plus k. H and k is your vertex, all right? So these are the 3 different ways we can write our quadratics. It's important to be able to convert between different forms. If you want to go from like vertex to standard, you're just foiling this out and then kind of simplifying it. Other way, you're trying to get your vertex and then you're going to like write it into this form from standard form. And then obviously from factored form, you can go straight to standard form. So know how to convert between these different forms. Also, now we're going to move on to exponential graphs. So for exponential graphs, you just need to know for these, you don't need to know as much as quadratic. You just need to know that exponential growth functions are like this. They're in the form like y equals b, let's say that's your y-intercept, times r to the power of t, where your r is greater than 1. Exponential decay is like this, where your r is going to be in between 0 and 1, like I mentioned earlier. As long as you know that, you'll be good for exponential graphs. All right, and then finally our last topic is going to be like polynomial nonlinear graphs. So these are basically just knowing about like even and odd functions and their end behavior and whatnot. So like, for example, this is your x cubed function, and then your x to the 4th is kind of like this. What's important to know for end behavior, if your polynomial degree is odd, meaning it's like 1, 3, or 5, your ends are going to be pointing in opposite directions. And if you have an even polynomial, like with an even degree, your ends are going to be pointing in the same direction. We call that end behavior. That is very important to know. Also, you can figure out how many, like the degree of a polynomial by the number of turning points it has. So like for x to the fourth, we have 1, 2, 3 turning points here. So our turning points are always going to be one less than the degree of the polynomial. And I'm going to quickly touch on even and odd functions here really, really fast. So x cubed is an example of an odd function. Basically, you can reflect it across the origin, right? If you were to reflect like right at this point, you'd get the same thing. Like if you reflect it, you'd get the upper part of x cubed. As an equation, you can write it as like negative f of x equals f to the f of negative x, like this. Basically meaning if you were to plug in negative x for x in the original function, it's going to equal a reflection over the x-axis. And then y equals x squared, that is a good example of a even function. So even functions, they are reflected over the y-axis. So you have the same thing on the left as you do on the right. You can write it in equation form as f of x equals f of negative x, meaning if we plug in negative x for x, we're going to get the same f of x function. So these are important to know. This is even, and this is odd. So yeah, that will do it for the advanced math section. There was a lot that we covered in this section, in this content area, and a lot of it is important to know. These are like higher order algebra kind of things. So make sure that you have gone over each of these topics, make sure you understand them pretty well, and you guys should be good with this section. So thank you guys so much again for watching. Sorry if the video is super long, but again, I'm trying to go over all the topics as much as possible in a comprehensive way. Be sure to like and subscribe if you enjoyed the video. Please let me know if you have any questions at all. Thank you guys so much again for watching, and I will see you all in the next video.